Okay, so here are some notes on the idea of this resting membrane potential. And I'm just going to be using this board. So let me write out a few of these. The idea of this resting membrane potential is that it only occurs at the surface of the cell. So if this is maybe it's a muscle cell, any kind of cell, the resting membrane potential is only on the surface. Only on the surface of the cell at the membrane. So the idea is that it's positive on the outside of the cell, the charge difference, and relatively negative on the inside. And this goes all the way around the entire membrane. Positives on the outside and negatives on the inside. So it's only at the surface. It's this very thin film, if you will, around the membrane. So when we talk about this resting membrane potential, we're only at the membrane. We're not deep inside the cell. Not deep in the cytoplasm. Doesn't apply to anywhere other than right at the surface. It's just a very thin little electrical potential across that. And the inside is slightly negative relative to the outside. Abbreviate negative relative to outside. And the amount is the difference, the potential difference is approximately minus 70 millivolts. So it's a difference of about 70 millivolts between the outside and the inside. And the inside is negative relative to the outside, to about that much. The other thing to note is that most cells, the membrane is polarized. So let's say most cell membranes are polarized. I'll abbreviate membranes are polarized. In particular, those that we're going to be spending a fair amount of time looking at are muscle cells and neurons. They're both said to be excitable tissue, and we're going to excite them by altering that resting membrane potential, causing it to change polarity. All right. The other thing to keep in mind as we go into this story is the relative concentration of ions inside the cell and outside. So let's say, remember relative ion concentrations inside the cell and outside. So if this is our cell, high on the outside, there is relatively more sodium than inside, chloride, ions, calcium, and bicarbonate, HCl3 minus. So there's relatively more of that outside the cell than inside. High inside the cell. Gone over this. Potassium. Most of the potassium is stored inside the cells. Something to note regarding calcium is that cells can store calcium, but it's not free floating in the cytosol. If the cell is storing calcium, they store it in the sarcoplasmic reticulum, not free floating in the cytosol. So stored in sarcoplasmic reticulum, or BSR. And I'll be looking at that at various times, particularly with muscle cell contraction. Because you remember earlier,
That's calcium that's stored, right?
yes, I'm sorry, calcium stored in the sarcoplasmic reticulum. So we'll be looking at that when we talk about skeletal muscle contraction. All right, so on to the resting membrane potential. How is it made and how is it maintained? Keep in mind that we're only describing the picture at rest. We're just setting up a polarized resting cell membrane. We'll later on go to depolarize it and create an action potential. But right now we're just getting it set up at rest. So here is a piece of the cell membrane. We'll get oriented. So here's the extracellular fluid, and this would be the intracellular fluid, or the cytosol. And you know the difference between cytosol and cytoplasm? That would be key vocabulary. So, the main player for creating this is the sodium-potassium pump, which I'm just going to represent as a cylinder. I like cylinders. This is a membrane protein complex. It's an integral part of the membrane. So it's an integral membrane protein. So this would be our sodium potassium pump. Your text may be describing it as the sodium potassium ATPase. It's the same thing. ACE, of course, is denoting an enzyme, and substrate is involving ATP while it's doing this pumping of ions. So they're the same thing, sodium potassium ATPase or sodium potassium pump. And as it's running, it pumps 3 sodium ions outside the cell and 2 potassium ions inside the cell. That sets up that relative concentration difference that we just had on the board. Higher sodium on the outside, higher potassium on the inside. This is all at rest, right? And it's only occurring right at the cell membrane, which is where our membrane potential story is going on. Now, this requires energy because you're constantly pumping sodium out of the cell to where it's higher. So you're going against a concentration gradient. The same with pumping potassium in. So it takes work. It's a type of primary active transport, meaning that ATP is hydrolyzed. This is a critical part of the story. However you want to represent that, I like to just draw, a little arrow, and it gets hydrolyzed to ADP. And if you want to keep track of the other phosphate, you can just put it like that. That represents ATP hydrolysis powering the pump. This is an example of primary active transport. That should be familiar. Okay, so what have we gotten so far? We've created an ionic gradient, a chemical gradient. You see it? More sodium on the outside than on the inside, more potassium on the inside than the outside. So there's a concentration gradient of those two ions across the membrane. You already knew that from our relative ion concentrations. So one way of looking at this, you know already the charge on the outside is positive relative to the inside. And one way that it sort of makes sense is just to look at the number of ions that are pumped. More of these positively charged ions are pumped to the outside than pumped to the inside. 3 cations going out, 2 cations coming in. That makes sense that the outer membrane is more positive than the inside. That's not what produces most of the resting membrane potential. Most of that minus 70 across the membrane, say approximately minus 70 millivolts, most of that minus 70 comes from potassium leakage. So there are leakage channels in the membrane for both sodium and potassium. But we're concerned with this story primarily with the potassium because a lot more potassium leaks out than sodium leaks in. So we can sort of forget about the sodium leaking in to start. So let's put another protein in here, another integral membrane protein, and this is a potassium leakage channel. The idea is that it's just open all the time at rest, and potassium is constantly just leaking through it. Which way is potassium moving? Good. It's going from where there's more potassium to where there's less. So more potassium diffuses out through that leakage channel. That's a major component of this minus 70. So, now check this out. The only reason potassium is flowing in that direction is because of the gradient, right? If we change the gradient, we're going to change the amount of potassium. That makes sense? Okay. That's basically it. So if I ask you to describe this, I want you to talk about the sodium-potassium pump creating this chemical gradient. It's primary active transport, so make sure that you mention the ATP hydrolysis, the 3 sodium out, 2 potassium in. That sets up the chemical gradient. So that then the potassium, is the other major piece of the story, can leak out through these potassium leakage channels. And as the potassium leaks out, you're taking the positive charges from inside the cell and putting them to the outside, and what's left behind inside the cell are large anions. Large anions and proteins that tend to be negatively charged. So what's left behind are negative charges along the membrane. So once again, this story of creating and maintaining this resting membrane potential is only occurring right at the thin film of the membrane on the outside. Deep in the cytoplasm, we don't talk about it being minus 70.